Hello and welcome to another edition of Physics 264 pre-lecture tutorials. I'm Dr. Steve Brule. Today we're going to study integrators and differentiators and get ready for the lab this week. First we'll derive the equation for the op-amp integrator. Then we'll show how to test the integrator output voltages against theoretical predictions for sine wave and square wave inputs. We'll test the relative phase of the output of the integrator in relation to the input to make sure it's what we expect. And we'll derive an equation for the op-amp differentiator for the theoretical version. And then we'll test the differentiator output voltages as well as phases in relation to the theoretical predictions for sine waves and sawtooth waves on the input. Well, let's take a look at the integrator circuit theory. I'm going to go through this fast because you've already done this in the lecture. From the golden rule number 2, you know that these two inputs on the op-amp have to be identical if the op-amp is operating. And since this is on ground, we know this is going to have to be a virtual ground at V equals 0. From the definition of capacitance, we can find the voltage across the capacitor is this. From the definition of current, we can integrate both sides to find an equation for the charge, which is what we need right here. And we substitute that in for here, and we get an equation for V out. From Ohm's law, we know what the current is through the input resistor. It's just the voltage across the input over the resistance. This is the virtual ground. This is the input, so that's the voltage drop. There we go. And from the golden rule number 1, we know there's no current that goes through that input on the op-amp, so all the current that goes through the resistor must go through the capacitor, and then we can then assume that the current through the capacitor is the same as what we just calculated. Substitute that in for the current that we were integrating for charge, and we get the output voltage for the integrator. And this is the equation that you derived in class. Okay, well, let's test that equation with the our laboratory equipment. So first of all, we have to set up our op-amp. As usual, we put our negative supply to pin 4, positive supply to pin 4, 5, 6, 7. It has to go along these rails. We're using red for positive, black or blue for the negative terminal, and our negative rail, and black for the ground rail. And notice that the ground rail is connected to the output terminal here, where we're going to share all those grounds with our external equipment. Okay, we are going to put the positive terminal here to ground. So there, the positive terminal is pin 3. We put that to the ground rail right there. The output is connected to pin 6. So here it is coming to that green wire, and that's going to be our output terminal. We need an input resistor, so I put the input resistor right in there. We've got a yellow wire going to an output terminal, and that's where we're going to put our input voltage into the integrator. Well, we need our capacitor that goes across pin 2 and 6. There it is. And we've also got a resistor that's going to be in parallel with this capacitor, and that resistor is there just so that when you have an integrator and it's not in a loop, then it will integrate any tiny little voltage on this input, and the output is going to go and saturate, and we don't want that to happen, and this keeps it from doing that. Well, these resistors are not needed that were in the lab book, and we're just going to omit that for our lab this week. The signal from the frequency generator goes to the input of the op-amp. So here it is, frequency generator coming to the input of the op-amp. See, that one is the yellow. And then this wire here takes it to the channel 1 of my oscilloscope. The output of the op-amp is going to channel 2 of the oscilloscope, so I can get a dual trace here. And once again, this is my ground tree where all the grounds come together and share that common ground. Now that we've built our integrator circuit, let's test it for a common sine wave. So we're going to put a sine wave, and you just select sine wave over here so you know what kind of input you've got. So here's the equation we derived, and we're putting a sine wave in for V in. Well, what's the integral of some amplitude times the sine? We can take the this is another thing you derived in class. I'm going to go through it pretty quick. So the integral of the sine is 1 over omega times the cosine, and with a negative sign, so that gets rid of that negative sign. We carry the constant out. So then we end up, when we evaluate the cosine, we end up with this constant term, which we're not going to fool around with in our lab. So we're just going to look at this amplitude of the cosine wave. We can write this equation in terms of frequency. I'm not going to worry about that one, but I'm going to change that to frequency because that's what we're observing on the frequency generator. So I just, 2 pi f is omega. We're just going to forget about that, as I said. And let's see what the output we would expect using the experimental values that we've chosen. So I've got a frequency. This is not the frequency you're going to start with in the lab, but I'm just starting at 2057 hertz. And I measured the capacitance using Buzz's WaveTech capacitance meter to get it very accurately. It's supposed to be 0.1 microfarad, but we measured it more accurately to be 0.93. They vary quite a bit. Okay, so first let's vary. Before we start measuring the voltage, let's check the phase. So let's verify the output is a cosine wave if the input is a sine. Well, is that a sine wave? Well, it is if we pick a point right here. We can arbitrarily pick wherever we want for our initial time. And then I'm just running that up here. So this is the initial time. So if this is our sine wave, then it looks like a regular sine wave, then this becomes our cosine wave. And sure enough, it's in perfectly 90 degrees phase shift, as we would expect. So the cosine is 90 degrees from the sine wave there. Okay, let's measure the input and output voltages. And unfortunately, throughout this video, I never centered my waves, so the center line is a little bit off. So we are going to measure from this center line in every case up to the top and then to the bottom, and then we add the two and divide by 2, and we'll get the average amplitude. So that's how we'll be doing it through the whole thing. And that happens commonly when we do our experiments. Sometimes it's not perfectly oriented. So I've got 0.4 divisions here, 0.8 divisions here, and I've got it at 0.5 volts per division. So I end up with this amplitude is 0.35 volts. That's this the amplitude right here. And I measured now the output voltage. I've got 0.4 divisions on the top, 0.2 on the bottom, and I get a 0.03 volts amplitude for the output of my op-amp integrator. Well, let's calculate what we expect. Here's the equation we derived. I just plugged in all the values that we had, the input voltage of 0.35 volts and my driving frequency, the resistance and the capacitance. And I get an amplitude of 0.29, and we measured 0.03. That is excellent for measuring from an oscilloscope because they're usually off by 10% or so. Let's change the input frequency and see how the output changes. So we've changed our input frequency to 639 hertz, gone down quite a bit. Well, what we would expect theoretically, I've just plugged that 639 hertz into my equation. I would expect an amplitude of 0.094 hertz. No, 0.094 volts. Let's see what we get. And I measured it right here, and look at that. It's 0.095. Wow! I wasn't even trying that hard. Well, if we put a square wave on the input, what would we expect? We would expect a sawtooth. So here's the input here is a square wave. We're integrating it. We're integrating a constant, and it just goes up. And then when we integrate this, it goes down. So we expect it to go like that because that's how the integrator works. But what's the amplitude of this sawtooth? We know it should look like a sawtooth, but what should the amplitude be? Let's work that out. So now our input is a square wave. So now for our input voltages, we're going to put the square wave. Well, a square wave is just a constant voltage up, and then a constant voltage down, and a constant voltage up. So each one of those is half of the period of the square wave. So that's why I'm integrating from 0 to t over 2 of some amplitude, and we're going to do the negative amplitude so that these negative signs cancel. We end up with a positive sign at the end. It's just a little nicer that way. So if we integrate a constant from 0 to t over 2, we just get t. We evaluate it from 0 to t over 2, and then we end up with this equation for the output voltage that we would expect if we had a square wave. Or in terms of frequency, so this was the period of the, we were looking at half the period of the square wave. Well, instead of t, you know that t is equal to 1 over the frequency, so I just put 1 over the frequency instead of t because we are measuring frequency with our frequency generator. Okay, well, a little note here. So this amplitude here that we're getting, the output voltage, this is the peak-to-peak amplitude that we would be measuring. So here's the square wave down at its negative value, and the integrator integrates, and then when the square wave jumps positive, then it starts integrating the positive and going negative because it's got that negative sign here. So this amplitude that we found is the distance from this is called peak-to-peak amplitude. So it's the distance from the lowest point of the wave to the highest point. So that's the peak-to-peak amplitude. So if we want to find the actual amplitude that we're used to measuring, which goes from the center line to the peak, then we just divide this number by 2, and so that's why that's 4 instead of 2. So now we've got our equation for the amplitude of our sawtooth that we would expect. Let's measure what we get and see if it jives. So here's the amplitude of the input. I'm just measuring, the amplitude of the square wave, and the same way I've been doing it. It's at 0.5 volts per division, and we have an amplitude of the input of the square wave of 0.375 volts. I plug that into my equation, and I expect to see an amplitude of my sawtooth, that's just the peak amplitude, not peak to peak, because I got that 4 there. It's a 0.063 volts. Let's see what we actually measure. Look at this. I measured from here to here and here to here, did it the regular way. I got 0.065. It is right on the money. Physics really works, doesn't it? Okay, so let's go into the differentiator circuit theory. This is another thing you've done in lab, so I'm going to go in lecture, so I'm going to go through this really quick. Once again, since this input to the op amp is at ground, we know that this is going to be a virtual ground, that the op amp is going to maintain that input at 0 voltage because that is our golden rule number 2. From the definition of capacitance, we know the input voltage is equal to the charge on the capacitor divided by the capacitance, Q equals CV. That's easy. From the definition of current, we did that before. I'm not going to go into that. So now we can we have this equation, this integral equation for charge. We can substitute that in for charge into this equation, so I end up with the input voltage is equal to 1 over C times the integral of I dt. So how are we getting a differentiator out of this? You'll see. I'm differentiating both sides of this. I get this equation because the derivative of an integral is just the argument there. Now I've just solved this equation for I, just multiplied both sides by C. So now I have an equation for the amount of current that's going through the capacitor, and there's our derivative of the input voltage. By the golden rule number 1, we know no current is going to enter the op amp, so all this current goes through here, so this current is the same as that current. By Ohm's law, the voltage across this resistor, this starts at 0, so this must be minus IR. And since we have this equation for I can substitute this for I, and I get this equation for the output voltage of my differentiator circuit. So let's test this differentiator circuit. Here's the equation. Is it good? Well, first of all, we have to hook up our differentiator circuit. I'm not going to go through the steps of that because you can do that yourself. These resistors in the lab book are not needed, and we will not be using them. Measure the input and let's measure the input and output voltages. Here's the input and there's the output voltages for a sine wave input. So I just did that. Here's our input voltage that's the sine wave on our input of our differentiator, and then here's the output of the differentiator, and I've got the amplitudes of those two things using the usual way. Well, here's the equation that we derived for the output voltage of our differentiator. Well, what's our input voltage is some amplitude times the sine of omega t. What's the derivative of sine? It's just the cosine times the derivative of that inside the parentheses there. So that's why we got the omega out in front. And there's the constant also came out in front. So plugging the numbers in for RC, the amplitude of the input, which we measured, it wasn't that 0.7. Let's just check. Yep. See, wait, I'm going too fast. This is 0.7. There's the amplitude of our input. Okay, so there's the amplitude of our input. Omega is 2 pi times the frequency. I just kind of skipped that step. And there's our cosine wave. So we expect an amplitude, plugging all these numbers in here, we expect to see an amplitude of 10 on our output. And what did we see? 10, right on the money. We should be getting awards for this. Is the phase correct? So here's a picture of that oscilloscope screen, and we know that the input is a sine wave, and if the output should be a minus cosine wave. Is it? So I put this zero line for our, is our zero voltage line, which isn't lined up perfectly. I wish I'd done that better. But that's about where the zero line is. And we expect then to see minus the cosine. So if it was a cosine, the cosine would be at its maximum value right there. But then if we take a negative sign, it flips it over. So it's almost right, but it's just a little bit late. Why is that? Differentiator is lagging a little bit. The op-amps don't work as well as differentiators as they do as integrators. And we'll see in this particular case, it's also quite evident. So we're putting a sawtooth on the input now, and we're looking at the output, which is going to turn out to be a square wave. Look how the output should be the derivative of the input. So it's the slope of this line. The slope of the line changes immediately. It's instantaneous changing right there, and the op-amp can't keep up with that instantaneous change and go up and be a nice square wave, at least at this frequency. If we slowed it down, then this part where it's trying to keep up, it gets compressed and you don't really see that, but I'm moving it a little faster than the op-amp wants to go. So we had a bit of a lag. Okay, I measured the input and output voltages for the input when we had an input of a sawtooth. So we're going to test those two voltages against the theoretical equation. Well, what is a theoretical equation? We haven't worked it out yet. Here's the what the differentiator gives us. The input voltage is some amplitude times a sawtooth wave. Well, what is the derivative of a sawtooth? It's very easy to figure out because it's just the slope of that sawtooth wave here. I was just thinking of that doesn't look like a very straight line here, and that might be why we're getting some lag too. I don't know. Okay, so here's this line. We want to try to figure out the slope of the line. Well, what's slope? It's rise over run. The rise is minus the amplitude here. So there's minus AN. And the run is this distance right here, which is 1/4 of a waveform. So the whole waveform goes from here to here, and that's 1/4 of the waveform. So I'm dividing by this is 1/4 of t here. That's 1/4 of the period. And I'm dividing the change in the amplitude by that, and that is the derivative. So I kind of did that in a sneaky way that made it very easy. These two negative signs cancel, and we end up with this 4 comes up on top, and then I changed, frequency is 1 over period, so I just put that frequency in there because that's what we're measuring. Plug all the numbers in that we had for that particular run. That we didn't have any number for that. But remember we had a 6.8 volt on the output. We got 6.4 that we our theoretical equation is telling us it should be. So we're just a little bit off on that one, but it's still very close. I hope you've enjoyed the show today. Thank you so much for joining us.